Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on CO2 sequestration modeling. And as usual, we will model everything with CMG software. It's a very powerful tool for CO2 geological storage modeling. All right, and it's been a while since we did this exercise last time. All right, but previously we have covered about the fluid modeling. We incorporate the mineralization, and we did that in WinProp. Okay, so after WinProp, now we need to deal with the builder. Okay, because we want to modify a little bit about the model. Okay, and I will start for mineralization trapping. I will start the model using the previous model, which is the CO2 storage that's already incorporate, of course, structural trapping, hysteresis trapping, and solubility trapping. Okay, so you just add the trapping one step at a time, starting from structural trapping. You then add hysteresis trapping, and then solubility trapping. And now I'm going to add one more trapping, mineral trapping. Okay, so it's almost the final step of the trapping that will permanently keep the CO2 in the subsurface. Okay, so this is my starting file. I already saved this file in another folder to keep the model until the solubility trapping. Now I just copy that file, and then the copied file, I'm going to rename mineral trapping, because we will add mineral trapping, okay, on top of the solubility trapping mineral. So mineralization like this. Okay, and let's say solubility Harvey, I will keep that name. All right, now we need to do some modification on the builder. Okay, so we will use the dat file for the builder and drop it here. All right. All right, so now we are inside the builder already. Okay, just to check our model here. All right, you see the wellbore here and the perforation, and this is our aquifer model. Okay, and then let's go to rock fluid, or maybe component. I mean component. Okay, and then here we have the rock type. All right, or if I expand this component properties, you can expand, right? Okay, and then you can right click and import WinProp generated model. Okay, this is the one that we need, because we already create the WinProp file that incorporate the mineral trapping or the mineral reaction. So click on that. Okay, so I just type in for the molality aqueous primary. You can follow me here, the value. And then I add volume fraction mineral anorthite, calcite, and kaolinite. This is the value. Okay. So, and then you control save, you save, and then it will be colored green here. Okay, let's see if we can explain something here, something that we already put on the editing. Okay, so you already know this for to stop or to neglect the vaporization of water. This is derivative for the reaction. All right, and then this is CO2, and then aqueous. All right. Okay, so maybe we can stop it here. So this keyword, and then we have this keyword. I just make a note about the components, and this will be followed by these values. Okay, which is the number of aqueous components. All right. And then these numbers represent the number of molecules. Okay, this is important. So these numbers represent the number of molecules of CO2 in each of these aqueous components. All right. So of course there is no CO2 in H plus, of course. There is no CO2 in Ca2 plus, all right? But there is CO2 inside this because we have one carbon atom from CO2 to this CO2 HCO2 3 minus, and some will go towards CO2 3 minus, all right? So again, this value, this number will show or will represent the number of molecules of CO2 in each of these aqueous components. That's why this ionization, it's actually another trapping, okay? Because it takes the CO2 from free phase or from the trapped condition to the ionized condition. All right, and CO2 MNR fact, okay, this keyword is followed by this 01 or 010. Okay, this is the number of the minerals. This number represents the number of molecules of CO2 in each of the mineral component. So you can say there is no CO2 goes to anorthite, goes to kaulinite, but there will be CO2 goes to or becomes calcite. All right. Okay, because in calcite you have CaCO3. All right, or maybe if you have dolomite, there will be CO2 also goes to and becomes the dolomite. All right, so that's what happens. And then in initialization section here. All right. So we have Z gas. That's why previously in the builder, I neglect when there is an option to use Z global, because in fact, we do not need Z global. We already have Z gas here. Okay. And yeah, gas zone, no oil. Okay. And then we put molality, aqueous primary in, and then this is the component, and then this is the molality. And for the volume fraction, anorthite, calcite, and kaulinite, it's like this. All right, and then let's see what do we have here? If you're interested, okay, maybe we can, yeah, after you add mineral reaction in WinProp, you will generate some keywords actually in this .dat file. And maybe we can, yeah, discuss about this. Okay, log chem equal coefficients, right? It's a bit complicated. Okay, actually it might be complicated, but it is calculated with a fourth order polynomial in temperature. Okay, yeah, whatever, we can just follow what the CMG gives for us. And then N-rate react. Do we have that? Maybe I can search it here. N-rate. And then react. I don't have that. Or maybe not here. If you're interested in, of course, we find Aquifer, right? Yeah, so Aquifer. Maybe I can explain this a little bit. So this keyword specifies that the aquifer is completely filled with water, Aquifer, right? It must be followed by on or off. If this keyword is not used or off is entered, okay, a small trace of hydrocarbon phase is always present in the aquifer. In fact, we allowed that to occur, to happen. All right, it actually helps us in the calculation. we allow a trace amount of hydrocarbon, methane actually, to exist, to be present in the aquifer. And then let's see, aqueous viscosity, all right, and then we use Castin. This is viscosity model for the aqueous phase. It must be followed by Castin for the Castin correlation in this case. And then maybe, do we have something called RF calc? Okay, so this is to specify computation of phase resistance factor caused by change in fluid porosity due to solid deposition or mineral precipitation, or or dissolution. All right, and then activity model. Okay, this is some keywords. Activity model B dot. Right now we can explain this here. So this is the activity model for the aqueous phase. It must be followed by a B dot or other options. Actually, there's no sophisticated explanation, by the way, based on the manual. So if you're interested, you can find it in internet what B dot is. All right. And then here, there chem equil. This is method for calculating the derivative of the chemical equilibrium equation. All right. It must be followed by either numerical or analytical. Okay, just like what we see in WinProp. Okay. So again, this is method for calculating the derivative of the chemical equilibrium condition. This one, their chemical. Okay, but for their react rate, this is method for calculating the derivative of the mineral dissolution or precipitation rates. Okay, so this is actually to calculate the derivative of the rate. In this case, the line 136, this is the method to calculate the derivative, of the, chemical equilibrium condition. Okay, again, for 137, it must be followed by numerical or analytical. All right, and then why accurate cutoff? Okay, this is mineral dissolution or precipitation rate are set to 0 if the mole fraction of the gaseous component in the aqueous phase is less than this specified limit. Okay, this is what we set in WinProp. Okay, again, mineral dissolution or mineral precipitation rate will be set to 0 if the mole fraction of the gaseous component in the aqueous phase is less than the specified limit. Okay, if you're interested, you can go back to my WinProp video. I already, say or talk a little bit about that. And then salinity, if you're interested, let's see. We have salinity where, okay, salinity calc. All right, of course, calculation for salinity in molality. It must be followed by on or off. And then what else? I think that's pretty much all. Do we have reactive? Okay, reactive surface area. Right, this is initial reactive surface area in meter square per meter cube. All right. Okay, we already input the value in the WinProp. And then log TST rate constant. Okay, and then I think that's pretty much all. Of course, if you want to really understand, you need to go to the fundamental first, especially the fundamental of the mineral trapping, CO2 mineral trapping. And then you also need to check the manual, the guidance in CMG GEM for CO2 sequestration case. All right, so far so good. Now don't forget to save. And as I said before, we need to go back to Builder because we want to add something to be produced in the result. Okay, so let's go back to Launcher first. Okay, and then let's go to drop our dot here onto the builder again. Okay, so now we are already inside the builder again. So let's see what we can do here. Again, I want to show you the IK2D view. And then what's important that we need to do right now is IO control. All right, simulation results. Here we will add some results. Okay, we can actually do that in the cedit, but sometimes it is more comfortable for us to do this in, in this builder. So the important thing here is the grid. All right, select grid variables. And then let's see some keywords that need to be activated. All right, I need to go down to molality, of course. I need molality of this. And then I also molality for the CO2, of course. I'm not interested in CO2, CH4. And then we also, of course, need the aqueous phase, CO2 3 minus, Ca2 plus, H plus, this one, and then this one. And then also for this one. I think all inlet. Okay, I need to make sure. Okay, so molality of this one, and then CO2. You can follow me, right? And then CO2 3 minus. Okay, good. And then H plus. All right, and then kaolinite. We need to go to mineral. Wait a minute. Okay, just be patient here. All right, mineral. Can we expand this? All right, mineral for the anorthite, mineral calcite, and mineral kaolinite. Okay. So again, in cedit, we will produce keyword called out srf, grid, and then I want to check it one by one. CO2, okay. H plus, okay. CO2, Ca2 plus, okay. SiO2, okay. In aqueous phase. This one, Al3 plus, OH minus, CO2 3 minus, okay, good. Bicarbonate, okay, good. Okay, so of course we already select the keywords that need to be activated, okay, so that we can get the result for the grid for these parameters. And then of course, click on OK again, and then save. Hopefully everything is good, and maybe we can recheck it on the cedit. Okay, so I will go to cedit. Okay, good. So now we are already inside the, the cedit, and let's see, now we have this keyword, good. Out srf, grid, we have mineral, anorthite, calcite, kaolinite, and all these aqueous component already inserted into our cedit. Okay, so now I'm quite confident to run this dot on the gem. Okay, and then I will stop it here, and then later on in the next video, I'm going to show you the result. Okay, so let's go and run it on the gem. All right, so the moment of truth, let's go drag the dot onto the gem. Okay. All right. Let's see. Still running. Okay, I'm going to pause a little bit and then I'll see you after the result has been perfectly produced. All right. All right, almost there. Later we will use this SR3, 95%, because it's mineralization. It takes, longer time to calculate. Almost done. All right, so I think it's finished. All right, completed. And now let's see. Yeah, we can check it, using Notepad instead. Let's see, I'm going to use Notepad. Okay, let's wait for a while. All right, so this is the result in Notepad. Actually, you need to open it using the .out, not SR3. SR3 is for the results, which later on we will show it. And we will use .out, and you see here, this is the results that you can evaluate. Maybe we can expand this. Okay, and maybe we can go to, I'm going to Control F, present in aqueous. Okay, so you see here, you can get the result like CO2 storage amount in in this day. Okay, and you can get the result like CO2 storage amount in reservoir, both in moles and in kilogram. In gaseous phase, no. Liquid phase, no, because we inject it in supercritical phase, so it remains in supercritical phase. We have some CO2 in the trapped condition. Some will be dissolved in the water. Some will present in aqueous ion. Some is precipitated, all right? And it becomes the mineral permanently. Okay, you can, of course, move, to the next time step, again and again, down to the bottom of the calculation, the last time of the calculation. Okay, of course, you can check the result later in the results. Okay, so this is the final result that we can have. All right, so I think I will stop it here. In the next video, I'm going to show you what happens or what can be visualized in results feature of the CMG. Okay, so I think that's all. I hope you enjoy this video. I hope this video is useful. Thank you so much for watching and see you again in the next Eng-Man videos. Thank you.